All right, guys, problem number 23, I have to be honest with you, is somewhat of a trick question. Okay, what's happening in number 23 is you've got what's called an oblique cylinder right here, or a slanted cylinder, so that what would I call this, like the center line of this cylinder that connects the center of the bottom circle to the top one isn't perpendicular to the base itself. This is not a right angle that's formed right over here. Now, that tends to freak everybody out just a little bit here, guys, but with this one, it's really not too big of a deal, and here's why. All of your cross-sectional slices are still going to be what shape? They're still going to be circles, and every one of those circles, you will notice right here, is exactly the same size. Maybe the best thing to think about with this problem is that you had a big stack of pennies. And if you put your stack of pennies in a nice pile like this is what they would look like. It would look like a right cylinder here where you just have a whole bunch of pennies stacked up like this. And together, that was ugly, that makes a three-dimensional solid, and it certainly has some volume to it. But now, you guys, what if we took the top of this stack and pushed it over just a little bit, and then did a little bit less of a push with each one of these pennies down there on the bottom, so that eventually this shape started to look like this shape? Now, my question for you would be, it's the same number of pennies, and each one of those pennies has the same volume that it had before. So have we really changed the volume of this stack at all from when it was a right cylinder to now when it is an oblique cylinder? No. The radius of the base is the same. The overall height is the same. That means that the volume is going to be the same as well. Now, once again, though, guys, you might look at this and say, wait a minute, I don't know a geometric formula for the volume of an oblique cylinder. It actually doesn't matter. You don't need it. What you need is a formula for the cross-sectional area. And what shape is each one of these cross-sections? It's a circle. And the formula for area of a circle, of course, is pi times your radius squared. So now you got to ask yourself, how big is the radius for each one of those circles? Exactly the same as this one right over here. So the area of each circle then is going to be pi times a radius of 4 squared, which is 16 pi. And what's unusual about this problem compared to almost all of the other ones that we've done, this formula here for the cross-sectional area is constant. There is no variable within this problem right here, guys. And that kind of makes some sense if you think about this as a stack of pennies. Every penny, of course, is exactly the same size. Its area for the face of the penny remains constant. It never changes. Now, I've always told you guys that is the hard part of a volume problem, because now we would say volume is equal to the definite integral of your cross-sectional area function taken with respect to x from a to b. Let's do the exact same thing here. Volume equals a definite integral, and a of x isn't really a of x. It's just a, which is 16 pi. It's a constant integrating with respect to x. And the limits of integration are going to be the lowest and highest values of x here. So we're running this thing from the base up until the top. We're starting when x is 0, and we're ending when x is 10. Now, the way I've kind of set that up, it's really almost more of a dy since I'm running vertical, but nobody cares about that. So this isn't too bad. Integrating any constant with respect to x is the constant, 16 pi, and you just stick an x at the end of that. And we're evaluating this from 0 to 10. Well, this is going to go pretty quickly, guys. This is going to be 16 pi times 10 minus 0, which of course is 10, and we're going to get 160 pi, and volume is going to be measured in cubic units, and that's going to be our answer here for problem number 23. And what I want to remind you then, guys, is the volume here would be absolutely no different if we were looking at this original stack of pennies here, 160 pi cubic units. It's exactly the same as if we kind of stagger that stack just a little bit right there on the right. It's the same number of pennies. The volume of each penny is the same, so the overall volumes need to be the same as well. So that 30-degree angle right here that probably got a lot of you worried when you saw this problem actually ended up having no impact whatsoever on the overall volume of this solid. So hopefully you learned something there. That's problem number 23.